So welcome to this continuation of the previous lesson. So here we'll just look at the Haber process in light of what we were discussing in the previous lesson. So we're talking about the position of Equilibria. So the position of Equilibria is important in determining the most economical method. So the Haber process is a process where we produce ammonia. We looked at that as an example in the previous lesson. So we are going to look at the conditions here that are the most economical in the Haber process. So this is the reaction, and we looked at it. It's an isothermic reaction between nitrogen and hydrogen to give ammonia. So let's talk about pressure. We said in the previous lesson, if you look at this equation, if you increase pressure, the reaction will shift to the right where there are fewer moles, and in doing so this reaction is going to reduce the pressure. So when you increase the pressure, this reaction is going to reduce the pressure by shifting to the side where you have fewer moles. Okay, so in this process we are promoting here the production of ammonia because we'll produce more of NH3. So high pressure will favor the forward reaction, which means a high yield of ammonia. The equilibrium will shift here to the side with the fewest number of molecules. And we also have to note here that the reaction is also faster when we increase our pressure here. So high pressure is going to favor the production of ammonia. However, we need to know that high pressure systems are expensive and can be dangerous. So a compromise is established where the pressure is 200 atm. So we have to settle for this compromise of 200 atm because of these reasons, cost and also the risk involved with using high pressure systems. Okay, so let's go to temperature. So you can see it's an exothermic reaction here, and we said in the previous lessons that if you increase your temperature, in this case you're going to favor the backward reaction. Why? Because this system is going to try and reduce temperature, and it reduces temperature by going for the endothermic reaction that absorbs heat. So the endothermic reaction here is the backward reaction. Because your forward reaction here is exothermic, we said it implies that your backward reaction is endothermic. So an increase in temperature will result in it will favor the backward reaction, meaning that a decrease in temperature will favor the forward reaction. So here high temperature will speed up the rate of the reaction as the molecules will have more kinetic energy. But which reaction are we talking about here? The backward reaction. The backward reaction is going to be increased because of your high temperature. So if we wanted to produce more of the NH3, we need to lower our temperature. We need a low temperature. Okay, so high temperatures will reduce the yield of ammonia as equilibrium will shift to the left, the endothermic side, to absorb the heat energy. A compromise is established if the temperature is too low. We have to establish a compromise here, because if the temperature is too low, the reaction will be too slow. So like we said here, in order to get more of the NH3, we need to lower our temperature. We need to lower our temperature. But in lowering our temperature will also cause the reaction to be slow. So we have to look for a compromised temperature where the reaction is not too slow, but at this temperature will also favor the production of more NH3. So there is a compromised temperature here, which is 400 degrees Celsius. So just remember these things and understand why we have to settle for these compromises. Why do we have to settle for these figures in terms of pressure and temperature? You have to understand the background in terms of Layers-Chatelain's principle. Okay, so let's proceed to talk about this. Another process, the contact process, which you can look at yourself, where the most economical method is settled for as well, but you have to understand the background. So Here's the reaction. The first reaction here, which is this reversible reaction rather, which is part of the contact process, very important. The oxidation of sulfur dioxide to sulfur trioxide is an exothermic reaction. So this is the reaction for which we need to look for the compromises. So I want you to just explore that on your own. So let's talk here about what affects the value of Kc. Remember, Kc gives you the proportion of your products versus your reactants. We saw in the expressions for Kc in the previous lessons that you say your products over your reactants. So a high Kc value means that you're going to form more products, and a low Kc value means that you're going to form less of the product. So you would want a higher value of Kc. So let's see what affects your Kc here. So temperature. Kc is only valid for one temperature. Changing the temperature will change the equilibrium concentrations, and hence Kc will change too. Okay, if temperature change causes equilibrium to shift right, Kc will increase. So if you shift towards the right, that is the production of more products, then your Kc will increase. If the temperature change causes the equilibrium to shift to the left, then Kc will decrease, meaning that you form less of the product. So like I said, generally you need a higher Kc value for such processes as your Haber process or your contact process. Okay, so let's look at this reaction that we just looked at previously, which is the oxidation of sulfur dioxide to sulfur trioxide, which is part of the contact process. So in this reaction, the forward reaction is exothermic, and the backward reaction is endothermic. We said that. So an increase in temperature here, the equilibrium will shift in the endothermic direction to oppose the increase in temperature, and this will cause what? Your Kc to decrease. Your Kc will decrease if you increase temperature. Why? Because the reaction is now going this side. We form fewer of the products. Remember, Kc is the proportion of products over reactants. And a decrease in temperature, the equilibrium will shift in the exothermic direction, and Kc will increase. So generally, you would want to increase your Kc in order to form more of the products. Okay, so just remember that temperature is the one that affects here your Kc. Okay, so let's move on to talk about the effect of concentration. So the value of Kc is unaffected by any changes in concentration. It's important for you to remember this. And catalysts, adding a catalyst has no effect on the value of Kc. A catalyst speeds up the forward reaction and the reverse direction, and the reverse reaction. A catalyst speeds up the rate at which equilibrium is established. So just remember that Kc is affected by temperature and temperature only. Okay. Let's talk here about pressure. So we're going to introduce here another equilibrium constant called Kp. So let's talk about the total pressure. The total pressure in a reaction is the sum of all pressures of the individual gases. So if you have a mixture of gases, the total pressure in that vessel is going to be the sum of the individual pressures of the gases, and these are called partial pressures of each gas. So you may be asked to use this information to answer questions like this one. We have this compound here which decomposes to sulfur dioxide and chlorine under heating. So here's the reaction. At equilibrium, the reaction vessel contains 263 kilopascals of chlorine. The total pressure in the vessel is 714 kilopascals. Calculate the partial pressure of this gas here at equilibrium. So let's look at this question, what we have to do. So we know the total pressure is the sum of all the partial pressure. So total pressure is going to be equal to the partial pressure of this compound here, the partial pressure of sulfur dioxide, and also the partial pressure of chlorine. So this is an important equation that helps us to determine the required partial pressure here. Okay, so So here we know that the total pressure in the vessel is 714 kilopascals. So 714 is equal to the partial pressure of this compound in question, plus the partial pressure of sulfur dioxide, plus our 263. We're told here that the partial pressure of chlorine is 263 kilopascals. Okay, so we know that chlorine has a partial pressure of 263. There is a 1:1 molar ratio with sulfur dioxide. So if you look at this equation, you see that there's a 1:1 ratio with sulfur dioxide. This is a product too. The partial pressure for sulfur dioxide is the same as your chlorine. So let's complete the equation. So we have determined here that our sulfur dioxide has the same partial pressure as our chlorine, because these are products which are being produced here in a ratio of 1:1. So we have 263 for our sulfur dioxide. So you must be able to use the molar ratios here to figure out partial pressures, as we have done here. So we can now rearrange the equation to find our partial pressure for this compound. So if you rearrange the partial pressure is going to be 188 kilopascals. Okay, let's talk about here mole fractions, why they're important. So the partial pressure of a gas is calculated using the mole fractions. We determined previously that there was a molar ratio of 1:1, but you can also use the actual mole fractions. And so a mole fraction is the proportion fraction of a gas in a gas mixture. So let's look at this generic equation 2D to give us E and F, which are gases. We have 4 moles of gas in total. 2 of them are D, so the mole fraction for D would be 1/2, which is 2 out of a 4 reduced to 1/2. So that's the mole fraction. So we're saying, what is the proportion of the molecules of D as a fraction of the total molecules that are there? So we have a total of 2 here, plus 1, we have a total of 4, and we have 2 of D, so 2 out of a 4 reduced to 1/2. Okay, so you need to know the following 2 equations when dealing with mole fraction calculations. You need to know the mole fraction of a gas, which is the number of moles of a gas over the total number of moles of a gas mixture, and you also need to know that you can calculate partial pressure here by saying the mole fraction of a gas times the total pressure in the mixture. So you need this total pressure of the mixture if you are to calculate partial pressure of a gas from its mole fractions. Okay, so let's look at an example. Here's an example question using the equations in the previous slide. 3 moles of this compound here, back again, are heated. The equilibrium mixture contains 1.75 moles of chlorine. The total pressure is 714 as before. What is the partial pressure of this? So if you look at this equation, you see that we have how many moles in total? 1, 2, and 3. Okay, so let's use this table to calculate here that initially we had 3 moles of this and 0 moles of this, 0 moles of this. Then change in moles. Remember this table. What is the change in moles? We know that we have 175 moles of chlorine at equilibrium, so the change is plus 175 here. So you have 175 moles. So 175 moles at equilibrium, the change would be plus 175. So to make this 175, how many moles of sulfur dioxide were also produced? How many moles of this were used? So you can do via molar ratios here, 1:1. So plus 175 here and minus 175 here. And here, once you subtract, you can calculate your equilibrium moles, which becomes our 1.25, 1.75, 1.75. So now that we have the equilibrium moles, the mole fraction of this compound that we're looking for here, this gas, is 1.25 here out of a total of 4.75. So if you add these 3, you would get 4.75, which is just the sum of all the equilibrium moles. And so the mole fraction of this gas is 0.263. Now, so we have to use the other equation that we looked at. So let's work out our partial pressure here, which is equal to the mole fraction times the total pressure. So this is how you would calculate using mole fraction. So it's important for you to be able to do that. So it becomes 188 kilopascals as before. Okay, so let's talk now about Kp, the equilibrium constant in terms of partial pressures. Okay, so partial pressures are used to calculate the gas equilibrium constant Kp. It's different from Kc because in Kc we use concentrations, but here we are using partial pressures. So a generic equation here, E moles of E plus F moles of F of gas F, G of G, H of H here. That's just a general equation. So the partial pressure for this system would be equal to the Kp rather is going to be equal to the partial pressure of G raised to the power of G, which is the molar fraction in the equation. The partial pressure of gas G raised to its molar its coefficient in this stoichiometric equation. So G, partial pressure of H raised to H, partial pressure of E raised to E, partial pressure of F raised to F. So the partial pressures are raised to their corresponding molar ratios in the equation, in the balanced equation there. So you need to take note of that, just like we did for Kc. So find the value of Kc for the following reaction and give the units, given that the partial pressures for gas A 324, gas B 162, and C 182, D 182 as well at equilibrium. So you just need to create your expression for Kp, which is equal to your products of your reactants. But see here that we have raised our A to the power of 2, is 2 here. Now we substitute and evaluate there. We realize that our Kp is 1.95 times 10 to the power minus 3. Then for the units we have to do the same as we did in Kc. Your units of pressure here times units of pressure for these two gases here, C and D, over your units of pressure squared times units of pressure, which is kPa, 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 and you cancel out and invert here. So it's going to be kilopascals to the power of -1. That would be your final units after inverting. So you must be able to calculate your units as well. Okay, so let's end here for today.